we'll start first by introducing you to a few approximation of Mie theory. You've seen when Meg showed you in the lecture today, she showed you several regions where there's approximation, like there's Rayleigh approximation for particle really small, and then there's other approximations. You get to bigger particles, and you get to geometric optics. So there's some analytical solution that you can plug and play. You can do yourself the analysis, and then there are there's the Mie code, which is just a series of polynomial bits, a term that you're adding up until you get to some convergence, and the convergence depend on how big your particle is until the solution. And then we're going to build, the results for population of particle and give you a little sense of how some of the graphs you've seen in Meg's talk this morning were created, and how they, and also an example from real life, which is why is fog so opaque? Fog is, there's not more, during fog, like this morning, there's no more moisture in the air than there is when it's raining. But because it's packed to a specific size of droplets, you suddenly can't see anything. So the one of the things that's interesting with scattering is that there's no conservation of scattering. In a sense, it's not, scattering per mass changes with the size of particles. So you get the most bang for the buck in a specific given size of particle, the most scattering. Take the same amount of material and you package it to different size particle, you can get very, very different results. Okay? And so we'll see how that comes out. It's basically resonance. It's when do you have the right size to particle ratio to get the most bang. You know it from drums, you know it from violins, you know it from acoustics. If you want to study zooplankton, you don't use optics because they don't have a similar wavelength. You use acoustics because then you can get a wavelength that's the right size to be commensurate with the size of the zooplankton. Okay, so that's kind of the idea. And that's why light works for phytoplankton, because it's the right size to resonate with the size of plankton, small plankton. Make sense? So, we'll start. So what are the inputs? You want the wavelength of light interacting with the particle, and you want them in the medium. It turns out it's not the same in air as it is in water. So the wavelength in water, because we care about water, will be the wavelength in air divided by n water times n air. So the ratio. So in our case, this is about water to air is about 1.33 or something like this. It's actually something like 0.75 times lambda air. And of course, n water is a function of wavelength, but for now we're not. It's a small function of wavelength. It doesn't, for this kind of measurement, doesn't matter. So wavelength in water is different than in air, and what we care about is the interaction in the water of the light. But we always report wavelength in air, because that's how we, when you talk about blue, it's what we can see with our eyes, and it's the wavelength in air. But it doesn't shift. Okay, so we have the wavelength in the water. Index refraction of the particle relative, index refraction of the medium, but what we really care is that of the particle relative to the medium. So we have a particle, and then, so the index refraction we put in was the particle divided by n of medium, which you can also, so this is if both of them are relative to air, but if you know the particle relative to water, you can put water as 1, and then you put 105 or 5. When you say 105, it's relative to 1 of water. If you did both of them relative to air, then this is going to be 1.34, and this one be 1.5 or something like that. Something like that. So as long as you're consistent with this ratio, you're good. And that, again, going back to our playing with light, this is really an indication of the change in speed of light between the particle and the surrounding. So So the wave that goes around the particle versus the wave that goes through. What would be their phase shift? That's what this determines. And then we have this weird thing called the imaginary part of English refraction that really has to do with absorption, but it has no n prime. It's the absorption if you had a solution all made of chlorophyll or all made of pigment, what that absorption would be. That is units of inverse meter times the wavelength. So that is units of meter or nanometer or 10 to the whatever, and then divided by 4. So this is your n prime. And these obviously should be in the same units if you knew this graph. Typically you don't know it, but you can derive it, and I'll show you how. Inversely using Mie theory, as you've seen from the work of Vico and Morel. So Vico and Morel in the 80s did a whole series of studies where they addressed how to model many different kinds of particle, bacteria, phytoplankton, different kind of phytoplankton, by inversely modeling them with Mie theory. So we talked before, you saw with, there's several ways by which you get output with these, one of which is the cross section. So a cross section is really how much attenuation. So we have cross sections. Optical cross section. So this could be optical. So it could be for A, D, or C, the optical cross section. And this is, you can think about it, about how much an optical property will you have if you had one particle per meter cubed. This is what you, I mean, that's an easy way to think about it. This is my beam attenuation. The cross section will be equal to having, if it's, I don't know what, 0.5, it would be what I'm going to get. It has unit of meter squared, my cross section, because it's an optical cross section, and provide amount of light that is attenuated, if it's the extinction one, by a single particle in 1 meter cubed. If we had n such particle, you multiply it by n to get in a meter cubed to get the beam attenuation. Well, the efficiency factor, as you learned from today, is simply the ratio of this to the geometric cross section. So Q is equal to these C's, A, B, or C, divided by pi r squared. So these are the efficiency factor, and therefore the unitless. So unitless, well, this is units of meter squared. And that's in okay. So our saving grace in all of this is that everything is additive. If I add something, you know, if I add a phytoplankton, if I take a phytoplankton and then add another one to the water or double my concentration, my optical property doubles. So everything is linear in this respect, and it's nice. We have these, I'll go down to the bottom because before we start to do the exercises, here we have what I told you about the approximations. So a brief survey of some analytical solution of Mie theory. Again, it's mostly, this comes, a lot of it comes from Van der Halst. We have it in the lab. That's a classic book about scattering by small particles. I'll use here lambda as diameter, as wavelength again in the medium. D is diameter or twice the radius. X is that size parameter, which is a non-dimensional relationship between the size of the particle relative to the wavelength in the medium. And again, so that determines the resonant interaction between the two. We have a complex index of refraction, which has a real part, which is the ratio of the speed of light, phase speed of light, and the imaginary one. And the reason we like to use imaginary because it's the decay. Those of you who are used to complex arithmetic, it's a decay for an exponential when you have imaginary, but you can, those of you who are not like complex, don't think about it, just think about the absorbing part. It's just that it's what people call compact notation, but you can also think about it as as confused notation because most people are not used to think about that in this way. This is the phase lag between the wave going around and the wave going through that you learned about today as well. So it's 2 times this x and minus 1. We have this optical thickness, so it's 4x times n prime, that n prime that you have over there, and then this beta again. And all this is simply because we're going to use them. They end up being part of your solutions. So Rayleigh scattering is the simplest one. It's when the particle is the smallest it can be. It was derived by Rayleigh in the 19th century. He did it for acoustics as well as for optics. You have, it turns out the phase function is exactly, and you saw it probably in Kurt, I'm sure he showed it to you. You have a symmetric scattering function around the particle. It scatters similarly backwards and forwards. And this is how it relates to the complex index of refraction. So yeah, again, we can square them. We can do a whole bunch of things with them. Rayleigh-Ganz regime is particles that are significantly larger in than the Rayleigh ones, but still smaller than the wavelength and are not very refractive. In both these cases, you can see that the absorption is proportional to lambda to the minus 1, but notice that scattering is proportional to lambda to the minus 4. So it's very steep with, this is scattering by aerosols. Turns out ocean scattering by molecule or by water is not exactly 4, it's minus 4.32, and it has to do with fluctuation of the molecules. That's Einstein-Smolakowski, while Rayleigh scattering really works well when things are separate. There's a lot of space between the different molecules as molecules in the air. Okay, we have the Rayleigh-Ganz regime. And we're going to only deal with one of those today, which is the anomalous diffraction. It was developed independently by van der Halst in the Netherlands and by Schifrin in Russia. But Schifrin wrote in Russian, nobody read it, what he wrote. So he did not get to be recognized for it as much as van der Halst was. And so we have simple, relatively simple. I mean, they look difficult, but they're not really. Once you determine beta, you determine rho, you just write it as this series of exponents, and then you can plot it as a function of wavelength or properties. So this is the efficiency factor for attenuation, efficiency factor for absorption, and by difference that of scattering. And you'll notice that QA is only dependent on rho prime. There's no rho here. So in this approximation, the absorption does not depend at all on the index of refraction, at all. We know that that's not completely the case because we can see in the beam, we can see cases where there's some interaction. But for phytoplankton, that has been good enough for very long in terms of being used. Now, why were these approximations useful? They were useful at a time where computers were not fast. Nowadays, you can say, oh, no problem, I can run my Mie code. But these are also useful because your Mie code might have a bug. So you may want to check it against these. So it's still useful, and it's useful to get a little sense. Geometric optics, your particle is much bigger. Now you're looking at shadows and seeing things of that. So there's this Babinet principle where what you're getting as attenuation is not simply your shadow, it's twice your cross section. And that's something that's really important because it's extremely useful to think about in terms of when you're comparing size distribution to the attenuation you're measuring with your instrument. So it's something that's easy to calculate and easy to see just on the tip of your fingertip. Is my size distribution consistent with the optics I'm measuring in the water? And how you move from one of those to actual IOPs is what we're going to do here. So we're going to start with a very simple exercise, this one, okay? This is my particle. We're assuming a phytoplankton. Its diameter is 2 micron. Wavelength is 440 nanometer, so we're in the blue. And the index of complexity complex index refraction 1.5 plus 0.01 I. So this is the kind we expect in absorption bands. So 440 is an absorption band with chlorophyll absorption. This is consistent. So first, what analytical regime is applicable for such cell? So for that, we'll have to compute these different x, rho prime, all those things. So let's start with that. What is our x for this particle? What is our rho? So we can decide what regime. So how should I calculate x? The size parameter for this. Look at tell me what I should do here.
I times 2 over 440.
5 times
2.
2.
You convert the units so they're both in nanometers?
Yes, you want the units of both the wavelength and the size to be the same. So wavelength, we said lambda in air, and it's 0.44 micrometer. And its size, we say, if we use diameter, the diameter is 2 micron. So tell me what to write. So, tell me what, I want to calculate x. Tell me what should be on
Divide
top
by
of-
lambda.
What?
Divide by lambda.
Divide by lambda, so 0.44. That's it? Is this in the median or is this in air?
It's an error.
Ah, right. Multiply this by 0.75. So what do I get when I do that? What x do you get? What?
About 19.
About 90. Units?
Less.
That's well.
Good. Units. Physicists will always like units stuff because then they're less confusing. Okay, so now phase shift around. What do we have here? So we have n minus 1. We have our x. What else do we have? Is it 2 x's? Remind me. 2x? 2x and minus 1. So n is 1.05. 0.5. Oh, sorry, this is going to be 0.05 times 2, so 0.1 times x, so it's like 1.9. Is that correct? Something like that. Or is that, so 2 x's times, so 2 times 0.05 is 0.1, 0.1 times 19 is 1.9. Is this okay?
Where did you get n?
N is so the n of the particle we said is 1.05 plus I times 0.01. So this is my absorbing particle. This is my index of refraction relative to water. Because I'm in water. It's in the beginning, it's here.
So actually, you wrote down.
Sorry, I write it as M. M equals, sorry, you're absolutely right. This is
M.
M, this is M, this is N, this is M. Sorry, that's what's right. Thank you. So we have a row of the order of 1, we have an x of the order of 19. So now let's look at for each approximation, there's some, at the top, for each one of them, I say something about what ranges of these are going to work for that approximation. So if you go to the bottom, to the appendix of this, we can see if Rayleigh, is it consistent with Rayleigh? No, because x needs to be much, much smaller than 1. And our x is 19, not here. Rayleigh-Ganz regime, rho needs to be much smaller than 1, and we have 2, 1.9, so it's not this one. Van der Halst, x can be significantly bigger than 1. We have 19, that's good. And this has to be much smaller than 1. So we shouldn't be very refractive. So 1.05 is pretty good in that term. So I think we got it. And we're not in geometric optics because our X is not hugely bigger than 1. It's bigger, it's significantly bigger with 20, but we're not in the thousands. So this is the one, surprise, surprise, that a lot of people have used for fiber path. So now let's calculate it analytically. So for this, we need to calculate rho. We need to calculate beta. We need what? So rho we have, beta we don't have, and we need rho prime. And we'll calculate QC, QA, QB, and then we'll compare it with the Mie code. Okay? Everybody's on board? Stop me because otherwise I run. So, okay, so let's calculate what beta is and what rho prime. We have the X that we can. We don't need X specifically, but we need rho. So rho we have, it's 1.9. And if I make any mistakes, you tell me. So because some people would just look at that. And so now let's calculate what beta is. Beta and rho prime. Okay.
Baby,
Rho
baby,
prime.
black and blue, I hate complex numbers without you.
Rho prime is 4 times nx times n prime. So it's equal to 0.04 times 19.
And from 0.01.
Yeah, times 4
Oh.
times x. So this is about 0.8. Right. About 0.8. And we have beta. Beta is the inverse tangent of n prime over n prime over n minus 1. So this is the inverse tangent. In our case, 0.05 divided, 0.01 divided by 4.
Is that in radians or degrees?
That's in radians. Because physicists work in radians. So it's the inverse tangent of 0.2. This is simply 0.2. So anybody knows what that is? 0.197? Yes.
I'm confused by n prime, it's 001.
0.01.
0.01, okay.
So
So we don't take the imaginary.
we don't take the imaginary, yeah.
No, there's no I. You don't use the I.
Oh,
Sorry. So this is n plus I times n prime. Good question. No. Everything is real.
Wait, so it's 4 times.
so
Except you can write the electromagnetic wave as cos plus I sine, and you can write it as an exponent, and that's when DC comes in. Yeah.
so M has a real and imaginary part, but N prime is a real number.
It's
It's a real number.
It's a real number.
Okay, okay.
Sorry.
Oh, did you round for me? No. Row.
You can tell me exactly what it is. What did you get? 76?
Yeah.
76.
That makes more sense.
So now we have all the components we need to calculate. Yes.
It was roll time, is
Yeah.
that 4 into
4 times x. I'm just copying that from there.
Oh, that's x, I thought it's multiplication.
4. My handwriting is horrible, but at least it's all times, and you have access to this text.
And it's a product. X
It's
is
a
not the
Yeah, it's not times.
symbol.
Yeah, they had to, when I did my baccalaureate in Israel, they had to copy everything I wrote after me because nobody could read what I was writing.
Very amazing.
I improved with time. Now a few people can. So now that we have all these, we can substitute them into these QA, QB, and QC. So now what I want here is to, and I know it's tedious, but it's very easy to code. QA. So now the question is, what are the efficiency factors? And again, the efficiency factor is the ratio of the optical cross-section to the cross-section of the particle. Yes.
Is it cosine of beta divided by rho? Or is it
Cosine of
cosine
beta
of
divided
beta?
by rho. Sine of open brackets rho minus beta.
Okay.
Cosine of beta minus rho, the tangent of beta. Here, cosine open brackets rho minus 2 beta. And I checked it yesterday, so, and this is cosine of beta divided by rho, all that squared times 2 times cosine 2 beta. So, anybody want to throw out what they got?
Not there yet.
1.42.
What?
1.42.
1.42 for QC.
If I didn't type it. We'll see. Somebody else should do it.
You're wicked
What do you get for
fast.
point for,
I'm not there yet.
what do you get for QA? And I can go to,
If you don't have MATLAB, you can do this in Excel, which is.
QA is 6.1628.
no way, Jose.
No way? Okay,
No.
something has gone wrong.
So the thing is, what do we know? And this is where it's intuition that's built over years will tell you. QC for very large particle is 2, and it's going to go to 0 when the particles are really small. So it can be in certain specific size distribution bigger than 2, but overall it's bounded. Same QA will relatively monotonically rise to 1 from 0. So when you tell me QA of 6, I know it's 10, which is not existing. And similarly, QB will be the difference between these two. So it should be bounded. It might overshoot initially, but then it's going to go to 1 in the geometric optics or 2 if it's a non-absorbing part, exactly non-absorbing, which doesn't exist.
I have
One-
0.388 for QA.
I have 1.9. Sorry, 1.1988.
1.99.
1.1988
For which? For QA?
for
No.
QA.
I got
Okay.
0.38.
0.38 is more like it.
Her sounds reasonable.
What I remember from yesterday. So it's 0.38. Alan seems to get something that's consistent with what I got yesterday. But everybody, if you don't get that, please say so.
Yeah.
Alan makes mistakes, just like I might have made a mistake yesterday. I want to see my history from yesterday. I see my history. This I should close.
Yeah.
Layout. Let me see. History. Command history. There it is. So here I ran it yesterday. Let's see what I got. So I got 1.549. I got 0.3895 and 1.15. I'm not saying that I'm right. I'm just that's what I got.
It's 440 nanometers, and then you have to
you can see here how I wrote it. So here is the command history. You cannot, you can't, of course you can't. So, yeah, because I'm there. Here down the bottom is how I did it. So n prime, I call it n e equal 2, lambda 0.44, x, then rho prime, beta, and then I just wrote the crazy equation and how it came out. Now you also have those equations already written into a MATLAB file called ad.m. So you can, where you can input straight the If you look at ad.m, you'll see exactly all these equations already. So in ad.m, if I open it, it's here. Where is it? Ah, it's opening here. It gives you QC, QA, QB if you give it the size, lambda, again, both in the same units, n and n prime. It will calculate for you this. What? I got this. I got 0.38, yes, 0.3895 and 1.5491. But I divide by 1.34 instead of multiplying by 0.75. It would be slightly different than the QB of the difference. Okay. Any questions on where we're at now? And if you use MATLAB before, you can simply run this function. This function AD, you can run AD. We can do this here. We can just copy this. I can copy this here and put in 2 here. Here, put 0.44 times 0.75. Here I'm going to put 1.05. And here I'm going to put 0.01. Much easier. Wavelength in water, always in water.
But it doesn't calculate for you.
So that's much easier than having to print all these equations. If I just run the AD code. But next we want to see if it's a good approximation. So we're going to run the code, the Mie code, with exactly the same parameters and see if we're getting something very different, or because we know this is an approximation, it's an analytical approximation to this series summation. So Mie cover all the ranges. You know, we have these ranges of approximation, and the Mie theory is really all the ranges, going from the smallest particle to the largest. Some people say Mie regime. I don't know what they talk about. That's the Mie regime. The Mie regime is everything.
They talk about it as big particles, that we only use rate for non-moving particles, right? The mean scatters. It's not.
Yeah, the Mie theory covers everything.
All scatters are scattered. All particles can scatter. If they're homogeneous spheres, multiple different equations.
Yes. Are we ready to move to the Mie code?
No.
You tell me when you're ready.
No,
we
I
got
1.5.
1.54.
I took out of that.
So here. I'll make the approximation closer. Yeah. Sorry. But For now, it's only numbers. By the way, Heather, we're recording it, so you're gonna have access to it. Okay, no problem. No, I don't think so. So for now, it looks like total obstruction, but soon we're gonna start counting cells in a meter cube, in a milliliter, and see that it gives us something that's reasonable. But before we do that, should we try and run a Mie code to see how close this is to what we get in the Mie code? Okay, so to do that, we have a function called call bh dot m. So I'll call bh, which is just, so it's a function I wrote to call the Born and Hoffman Mie code. If I do call BH, it's asking me, what's the real refractive index of the surrounding medium? What should I put here? What's the real refractive index of the surrounding medium relative to my sphere?
1.05.
What?
1.05.
Of the medium?
1.
1. I could put 1.34, but then I have to also do the phytoplankton relative to air, and I don't remember that one. So I put 1, enter. What's the refractive index of the sphere? So it's the real refractive. What should I put now? 1.05. Good. Next, imaginary refractive index of the sphere.
0.01.
0.01. 0.01. So in these Mie codes, we always assume that that the medium is non-absorbing. There are codes that modify to an absorbing medium, just so you know. But water is so relatively, again, it depends on the wavelength. If you're near infrared, absolutely. But in the visible, relative to the phytoplankton, it can be assumed as an absorbing. Radius of the sphere. Radius of the sphere. 1. The diameter is 2. In micron, as long as you're staying in micron. 10 to the minus 16 units. Now wavelength, same unit as the radius, so it has to be micron in the medium. And you can actually write here 0.75 times. You can write, you don't have to calculate it. So 0.44 times 0.7 can be an expression, I think. Let's see. Thank you. Now it's so now it's for the output. It's asking you how many angles do you want? An output of the phase function for your cell. Number of angles between 0 and 90 degrees. And if you put in 91, you're going to get an output every degree. So put 91. But if you put 181, you're going to get every half a degree. Name of the output file. Test. Because we all call, or junk. I like to call mine junk.dat. Test of that. Okay. Enter, done. So now we're going to go and open test.dat. So just open it, just do it here and see what we're getting out. There you go. Now in Math, oh, it opened it here. It did open it in MATLAB, but it opened it here. So this is what it tells me. Can I make what? So you want this one bigger. The font probably, anybody knows how to make the font bigger? Right click. No, for this one. How do I make the fonts bigger here?
And then the fonts on the left hand side.
Thank you.
And then over on the right, do it.
So 18. Apply. Yay. This better? Sorry. So and we can also, let's take things down. Okay. So now either you can take pictures if you'll see something. That's good because as I'm losing my sight, at least now I'll be able to read it. I have giant screens because I have. So is this clear? This part, the me part, how we put in the input with call VH. Pretty straightforward. Charlotte and Nick, you're on. This was easy. You got there? What? Yes. So now we have the output that came out. It's here, and here we can also do the font. Maybe. I know. Text options. Yes. Text options. No. I don't know how to do this. So these are the outputs. So what you have here, and we'll plot some of them. You know what? Let's open them in Excel. That would be the best. Let's open this in Excel. File, open, just so you can see. Next, finish. Because then you can plot things relative to. So here is Excel. Here's an Excel window. So now I'm going to teach you a trick that took me years to learn. I'm sure all of you know it, but I didn't know it at the time. How do I separate this type of text into two columns so I can plot them one against the other? You don't know?
No idea.
So you go to what?
It's a data text to column.
Yes, data, text to column, and then you tell it what's your delimiter, and you say delimited. The next is going to be by space. Next, finish. Yay! Now I can plot them. It's all these little tricks that if you don't know people, you can. A few years ago, way too late, but I can still use it. Here we also. So here we have the QA, and so here I have problems because this stuff. Let's see if I can just open it a bit bigger so you can see. What's that? What's this? What? Now I'm going to learn something else. Yeah, it's here. This one? This one? Yeah. So here it butchered everything. But these are the inputs. This is my image refraction, the imaginary. Here are my wavelength, radius, and size parameter, and this is the wavelength in water. Then I get my QC, QB, QA somehow made it somewhere else. And there's a QBD, which is this thing here. And that's this, these are the angle, and this is the phase function. So what I suggest is you plot it, because let's see how a phase function may look for a phytoplankton. So I'm going to select these. And then I'm going to insert a chart, and it's going to be an XY scatter plot. Yay! And this is your phase function for this one poor cell that you. And if I can here change it into a log axis, it will actually look like the stuff you've seen in the class. Where's my logarithmic scale? Yes. This is base 10. That doesn't have, ooh, and look at all these resonances that we saw in class today. This is wave but it's interaction of the outside and the inside. All these diffraction patterns. So this is the phase function for this one cell. And you can see how many orders of magnitude between front scattering, forward scattering, and back scattering. This is 6 orders of magnitude between this line here and the front. Okay? Sorry.
No, it's okay. I've done something wrong.
So this is angle. Sorry, this is in degrees.
The scale on the y-axis.
That's the phase function. So it's inverse steradian.
Before you log transformed it, it was order -3 or something like that.
Well, before I just couldn't see all this because it's so small.
Yeah, I was wondering if my output is like before log transformers, like ordered.
I didn't log transform. I just put a log on the y-axis. There was no log transform.
So if your first value is 3,
Oh yeah, the first value is 3. It's here.
right, so
So,
it's between 1 and 10.
Yeah, my output, my first value is 27.
now this is between 10 and 100. So,
Minus 700, right? Yeah.
so here are the values. If we go back up, here is the value for the 0. It's 27,
Mhm.
26. What? I wrote it in 98. Sorry. Born in Hoffman, it's in the book from 87. And there was in Fortran, I translated it to my when I started my postdoc. Because I wanted a code I can play with. And I was at the time I was working in my. Okay, so now let's start to combine these outputs with stuff we understand. So let's go back to the Word and see what it is so we saw that the values are not very different than what we got here. So now we have a population. Now we're talking 5 times 10 to the 4th phytoplankton per milliliter. Okay, so now we have a culture. Now, and let's see what absorption, scattering, and attenuation we expect for a culture of phytoplankton. Sorry. Oh. Okay. What? Any question? Sure. So you're ready for the next? If you're not ready, we can take that. So the next one is I have a culture of phytoplankton, and there's 5 times 10 to the 4th phytoplankton per milliliter in my culture, which is consistent with coastal ocean. These kind of numbers, not a big bloom, but healthy concentration. And I'm going to ask you to tell me, and they have the same properties as those we just did. So they have exactly these properties. And I have 5 times 10 to the 4th phytoplankton per milliliter. What is my A, B, and C? And backscattering for this. How do you do it? How do I go from this crazy Q stuff to absorption? That I'm measuring with an AC meter or with a spectrophotometer. So now we move out of this real, esoteric physics to measurements you do in the lab, and you want to know if it makes sense. I count with I have a Coulter counter or some other way, or a microscopy. I have 5 times 10 to the 4th. So this is my standard. Yes, sir.
Use that equation,
Which equation?
the one in the box to calculate the cross section.
No, so you have the cross sections. You have the QA, QB, QC, QBB from your meter. Multiply by n, okay, so I get n times q. What units does this will have? So these have units of number per centimeter cube. So now I'm multiplying number per centimeter cube, something that's unitless. Will this give me inverse meters?
No.
So what? So let's keep going. Well, so this says so far we have units of number per centimeter cube times units. So these are the units that if I multiply by volume, that's not going to count. What should I multiply by? What? Radius squared, which is really what are we at? But what is units of radius squared?
Cross-sectional area.
Cross-sectional area, exactly. So we multiply this by pi, if we have D, so it's D squared over 4. Okay, so this is, my A is gonna be this, QA, my C is gonna be N times QC times pi D squared over 4. But now, we need to be consistent with the units. It's really important, because these we have in microns, 10 to the minus 6 meters. These we have per centimeter cubed, but we really want per meter cubed, so that we end up with inverse meter, because that's what we measure in the lab. In the lab, we measure inverse meter. So let's try to make that work for us. So QA is unitless, no problem. But my N, I have this per centimeter cubed. How do I do it per meter cubed? So N is 5 times 10 to the 4th. 5 times 10 to the millimeter. How do I move it to a meter cube?
Multiply by, no,
Multiply
10,000.
by
10,000.
100,000.
No, by 100 you move just 1 centimeter to a meter. And you have cubed. And 100 cubed. 10 to the 6.
Oh.
10 to the 6. 10 to the 6 millimeters per meter. Okay, so 10 to the 6. Okay, so now I have 5 times 10 to the 4th, 10 to the 6. That's the number. Great. QA is whatever QA I got from the meat code. What did you get from QA? 0.38. No, that was from, oh, that's the, that was the right. What? 0.28 you got? 38, excellent. Times pi. Now I have diameter squared that have to be in meters. So 10 to the minus 6 squared. But I have, sorry, it's 2. 2 times 10 to the minus 6, all this squared. And all this divided by 4. 2 squares. And 2 is also squared because it's squared. So this goes out to the 4 below. Like it's good. 1 of the 10 to the 6 go with the 10 to the minus 6. Here I get, yeah. So what do you get? So 10 to the 4th with 10 to the minus 6, that's just 10 to the minus 2. That's 10 to the minus 2. I want to QA calculated with them. It's very similar. I used 4th grade. So 5 times 0.38 times pi. So this week's going to be 0.4. What do you get? 5 times 0.38 times pi times 10 to the minus 2. What do you get out of it? 0.38?
How is he canceling?
0.06 inverse. 0.06 inverse meters.
There's some more adjustments, but yeah,
Something like
something like that.
Yes,
How did you cancel all of the big powers out there?
because I had a 10 to the 6 here, then I had a 10 to the 4th here, so that's 10 to the 10. Here I have 10 to the minus 6 squared, it's 10 to the minus 12. So 10 to the 10 times 10 to the minus 12 is 10 to the minus 12. So is this consistent with what you got as well? So this is even low relative to what we measured at 440. So we probably had more doubt than that. You know, that also significantly.
Okay.
But it's the same order of magnitude. You know, within a factor. How about QC? How about the same calculation, but now you replace this 0.38 by 1.54 or 1.something. So you can divide what you got by 0.38 and then just multiply by the QC. What would you get? 0.40. Low but respectable. It's a kind of image anyway, should we measure? I mean, these are the kind of stuff we measure in the open. visit point. But now you can see how you move from, a crazy me calculation that you don't think, you wonder what would I ever use it for, to via microscopy where you count cells to actually getting optical properties. It's not that disconnected. Any question about what we did?
Biggest thing is to keep track of your units.
Yes, always.
Everything.
Yes.
Can you still do B equals C minus A
Because-
here?
Yeah, absolutely. It's
Okay.
always, so B equals C minus A, QB equal QC minus QA, et cetera, et cetera. And for QBB, it's one of your outputs. So you can actually calculate what your back scattering should be to these guys. When we'll do populations, after a break, we'll do populations, then we'll actually plot them for all the sizes. So you can see that. But before that, this is one of the most fun exercises, the next one. To me, it's
Pretty fun.
this one is really fun. So whenever we're done with the phytoplankton, but now we'll do populations in the side. We're all ready to do fog. What? Something unclear?
I lost something that I already did. It's okay.
No, tell me what.
How do you run the cal BH? Like what
Oh,
No, it's called BH.
call BH?
You put in input. It asks you. Call
Oh,
BH
oh.
asks you for input, and then you write.
You type it, it's gonna probe the question.
It probes you with questions.
Okay, perfect.
Yeah, you can just.
And you can modify the code so that is, when it probes you, it asks you specifically, like, what is your diameter in microns?
It's just an easy way to put it in. You don't have to use it at all. When we run population, it doesn't ask us. It goes straight to the BH code. So the next one I really love because that's the one that shows us that the mass specific response is a function of size. So if I take the point of the next exercise is to show us that we take a slab of anything and cut it to small pieces, depending on the size of these pieces. Even though mass is conserved, you can get completely different optical response. So size matters in optics. You take the same amount of material, same exact amount, just divide it to different sizes, we're going to get per mass. So dematerialization per mass, for example, that is going to change like you saw today in class with a resonance at a specific size. That's where you're going to get the most C per mass. And the example that I like simply because we saw it this morning has to do with droplets, with clouds. But you can it can be applied to marine environment just the same way as you saw today in Meg's. So with water in air, it's kind of funny because now the index of refraction is your environment as is air. So my n relative to air is 1.3. And I will assume that there's no imaginary part. So so how does this change C star, C over mass, as function of size? That's what I'm asking. For this is that. Yeah. Now, in order to calculate this, I can simply do dematerialization, which we said is equal to the number of drops times QC times pi d squared over 4. What else do we need? I think we have it all. And then divide by the mass. And the mass would be n, again, all the particles, times their pi d cubed over 3/4. No, it's over 6. Over 6. Pi d cubed over 6 times the density of water, which is 1 gram per centimeter cubed, or 1,000 kilograms per meter. So this is C over mass. And the n goes away. I don't even care about numbers. When I do over mass, I don't have to keep track of numbers because the numbers are in the mass as well. So the integration for mass, this goes away. In terms of d squared here and that is 1 over d. Pi goes away. And so it's really, it becomes a QC over d. And the density, and the 1 gram per centimeter cube without, again, you have to keep track of the units. So this is the calculation I want you to do, and you can run it through VHME. Please do. For diameters varying from 0.01 to 1,000 micron. So what we'll do, we'll divide it among you. Some are going to do 0.01. Some are going to do 0.1, 1 micron, 10 micron, 100 micron, and 1,000. Okay, and then we'll plot it. Yes.
So we don't use your setting time things the wavelength.
No, because you're in air. Absolutely right. And did I say yes? So you simply do 0.55 micron. So lambda is 0.55. Sorry, what it was? NQC 6. Sorry. This is just the volume. Yeah, it's the volume. It's the volume of the sphere. Yeah, it's 4 over 3 over 8. It's 4 over 3 pi is equal to pi over 6.
Yes.
Like, wait, is that
How do you get to like height is really-
Okay, so you guys are doing the 0.01, you guys are doing the 0.1 micron, 1 micron, 10 micron, 100 micron, and 1 millimeter. Or 1,000 micron.
So that's where you get the square root of the 6.
So this part is doing it for herself.
So this will have units of, let's use units of per meter per kilogram. These are going to be the units. Per meter per kilogram.
Then you do the volume. Or the mass of the jar, which would be the volume times the density, which is the mass of all
Oh, wait, 41.
Oh,
the water and then
So
of a drop.
So people use this for radius. It says diameter. So you want to use radius. If you use radius, put half of this. This is in diameter. Sorry. If it asks you for radius, put half of this.
What would you have? Oh, I missed that.
Yeah.
So for the refractive index of the spheres, it's not.
0. N prime 0. Your N prime is 0. Non-absorbing cell. So N prime is 0. And here for the density, we put 1,000.
That's our. Yeah. I'm gonna say
water is essentially 1.3, right? So it's still 1.75 times the wavelength.
No, we're not in water.
We are in water.
Water is in our air.
So you're doing this giant,
Yes.
this is a drop of
But
water.
isn't it going through the water?
Going through the air to reach our water.
Yeah.
For the number of angles. I think
Right.
It
it's-
doesn't matter, it doesn't matter. Whatever number,
Right.
we're not using that information.
Oh,
We're modeling fog.
But it's still interacting with the water. Is it?
So it's, yeah, so the particle is 1.33 relative to air.
Great.
So your N is 1.33.
The
Air is 1,
is the wavelength. The
0.55. You don't have to multiply
You
by
don't.
1.75 because it's, you're right, in the particle is different, but you're doing it in the medium. It's the wavelength in the medium.
Okay.
This is wavelength in the medium, so you don't have to multiply. 0.55 minus.
Oh, and then. Yes, so this is.
So you don't have to plot anything, you just have to calculate the C over mass.
Oh,
The
and
C
then
to mass.
oh, wait, but we're not using.
Right. What do I need to take out of?
So you beam attenuation just like you did before, and then you divide it by the mass. You can do the mass of the signal for it.
Yes.
All right, start again.
I get the QC it to be 1.18 times 10 to the negative 6.
Yes, 1.18 times 10 to the negative 6. And then what is QEX? Oh, no.
Q extinction and QEX is the same as QC.
Oh, okay.
Because some people, in atmospheric science in particular, they use the word extinction for QX. It's just conventions. This thing has decided to torture me.
Oh,
This decided
You
to
have a
feel
really small number?
we'll type something in. Give me a second.
I think it's just a big one.
No. I typed something in wrong.
How small is this number supposed to be?
How much? 1.6. 1.06 for what size?
0.1.
So for 0.1, we got 1.6.
1.06.
1.06. This is mine. Then we have 1,000. 100. 10. 1.41. This thing, this is this.
Oh, I forgot to multiply it by 1,000 with the denominator. That makes more sense.
Wait, it multiplies by 1,000, not minus 1,000? Oh,
I got 0.177.
0.177 for what size?
0.01.
0.01. You got 1.77?
0.1.
0.1. So 0.1 we're here at 0.1. That's for the 0.01. How about the people with 110, 100, and 1,000? We're waiting for you.
Is
This is the
in
density of
this.
water, 1,000 kilograms per meter.
No, I get that. Oh, you have to convert your radius into meters.
Oh, I need to add,
You can do it by just dividing by 10 to the -6. The whole thing. Because technically the diameters cancel out in the numerator, and there's only one denominator.
Point 0.17, okay, cool. Thank you. Oh,
Most of my undergrad was making sure you were units height, because they would give you these dumb engineering units. Like for power, and like it would be like in these like BTU hours, and then it's like give it to us in joules or like something like
useful.
useful, really useful.
Well, then give it to us in something like joules, which is useful.
Yeah. No, I don't want to say this.
I understand. Okay.
Yeah. A lot of my classes, because we didn't know how to do a problem, we just looked at the units and like, yeah, I'll just get to the answer in some way.
Yes.
Yes, I have solved problems by unit conversion before.
It's my favorite thing to do.
Really?
Well, no.
Yeah, so you're getting your Q back. That's your Q. This is your Q.
Okay. Given a water
So you're going, okay, so now you multiply it by pi, which is what you'd expect from geometric optics. Then you multiply it by the cross sectional area, divide by the volume, and divide by the mass. The density.
make sure that you're working in meters.
Yeah, make sure you're consistent in units. And yeah, in the end, you get something that has units of per meter per kilogram. So far I got values from only two groups. Okay, 150%, 115%, 1,000. Oh, 150. So that's here. 100. The 10 you're getting 150.
Mine is off by a factor of 1,000.
So how much? What should it be? You said
1,016. And the other way.
1,000.
No.
So it should be here. The point one is here. I don't know.
It should be much smaller. It's just like because of you.
Yeah.
But then.
Rewrite this.
No, now mine's small.
So we have 10,
Yeah,
we have
because I
100,
forgot to divide
we have
that.
1,000.
Yeah.
This is C in C per mass. And the units we stand are meter to the -1 kilogram. So are you still saying 1,000 there?
.177.
So far I have two values only. He's about what? What? The mass is volume of your volume of your particle times density of water, which is 1,000 kilograms per meter.
So I would find smaller values like this. For 0.1 diameter, I find 1 to the 10 to the -3. So 0.001.
So you're now
Much smaller.
that's
And Ellen will be a 5 for 0.01.
I got .177.
yeah, it's not consistent. Somewhere there, these two groups are not consistent. I'm not saying this is correct, but it's important to you.
I
What do you
used
guys get?
this equation.
Okay,
But there is no X.
so this D has to be in
Oh, E for X divided by the.
So
the
10
mass.
in kilo sorry, meters, which is 10 to the -6.
Yeah.
What was your
It's 2 times 10 to the minus 6.
Oh, no, what would you get for it?
So let me write it more simply for all of you. So I'm just going to divide. So there's a D down below. There's a 1.5.
I don't know much smaller.
1.5 times QC divided by D,
Oh, I
where D is in meters, and times 1,000. And where I went wrong, this should be meters squared per kilogram. This is my bad. This is in meters squared per kilogram. That's the correct.
Wait.
Well, I think you're,
Okay,
so
so
you're putting
your
it down.
QC is 2. Your QC is near 2. Your QC is this is going to be 2 times 10 to the minus 6.
Meters.
And this is going to be 1,000.
So I'm gonna give you
What?
just 2 times 10 to the -6.
Ah, yeah, the honey micro. Sorry, you're absolutely right. 100. Yours is 100 times 10 to the minus 6. There is 1,000 times to the minus 6.
Rand's 0.01.
Doesn't matter.
be in the
because
same-
it cancels.
Yeah,
You
to be
need
in
to
the same
have the
wavelength, yeah,
And that's it.
So guys,
yeah,
it's much easier.
yeah,
If
and
you,
then for this one.
if you simplify, you should have 1.5 times QC unitless divided by your diameter in meters times 1,000.
Yeah, I saw the same. I used a call view. I don't know if that one's different.
So if you have if your diameter is 100, it's 110 to the minus 6. If your diameter is 0.1, it's 0.1 times 10 to the minus 6. 1.5
Yeah.
times QC divided by diameter.
We have the same point one.
Meters
seven.
times 1,000.
That's not changed.
What is 4,700? 4,700? What size? 4,700. So you're here.
I used the call view function.
Okay, so at 1, I'm at 4,700. At 10, I'm at, we're moving it to 300. 300, okay, that's 300. That's 300.
I got threes of all orders of
I
magnitude.
used,
What?
So I did all of.
I used this.
And then I got
call view
three.
as opposed to.
Wait, let me pull it up.
Give me the one you were
It's-
assigned first.
It's this one, the
You were assigned 1. No, you were assigned 0.7.
Say this, and then it asks, and it does something a little bit more.
What?
0.3 times 10 to the negative.
I don't think so. What did you get?
Yeah, that's what I'm getting.
30.5 for the
Yeah.
100?
I-
30. This is 30.
No,
I meant positive fit.
We got it. 3.
3, 1,000, they got 3. Okay, so it's here.
Yeah, I'm on this.
So now I need the 0.1 and the 0.01.
3 and
Mine's
0.3 times 10
Still
to the
this.
fifth.
What?
3 and 0.3 times 10 to the negative.
This is 3. 4.1.
I'm sending it to you.
So you're not here.
The other one is 1 order of magnitude lower.
Something is not working correctly.
What is the difference between the call BH function and the other one? The one that was listed in the beginning? With the
AD,
QCs and the Q.
oh, the AD was for particles that are very close in heat refraction to water, like fiber.
Okay,
Okay, that's where we was. It's just an approximation.
okay,
While the cold BH and BH is the full solution
okay,
for any particle.
okay.
So I'm still waiting for the 0.1 and 0.1.
What I'm saying is just keep going up order of magnitudes. No?
Does 0.01 seem too low?
No. I'm asking for the value.
Oh,
That
point,
you got for 0.01. What did you get?
0.177.
Here you got 0.177.
yes.
Yeah.
0.177 is equal to 0.01. And I'm still waiting for the 0.1. Nick, what did you guys get?
There's not consensus.
So again, 1.5 times QC.
Yeah.
What's your QC?
0.07.
0.07, okay. Divided by 0.1 10 to the minus 6. Divided by 1,000.
abundance.
Oh, dang, what?
So
The same thing.
one,
Times 10 to the third.
one.
You got 1,000?
Yeah, 1.1.
So you guys get 1,000, so you're here.
Yeah.
So what we're getting is something that looks like the resonance curve I would expect.
Divide by two. Oh,
So we get a point here, and we might still have some uncertainties, but there's a certain size around a micron where you're getting the most, somewhere between 10 micron and 0.1 micron, you get the most bang for the buck. Now, Google, what's the size of fog droplets? From about 1 to 10 micron is the size of fog droplets. So it's right where you have the most bang for the buck in terms of attenuation per mass. Okay? So now you understand why it is that in fog and in rain you can see the cars in front of you, and in fog it's much harder. It's not because during fog there's much more water in the air. It's just that it's packaged particles that have the most attenuation per mass in size. And this is true for all the type of particles we looked at. So depending on how you take material P O C, POM, and you package it in different size particles, you're going to have a different response. And as Meg told you, but many particles are not just solids. There's aggregates, and then other rules apply. So this is for solid particles, not for
And the intuition for this is that it's the maximum like optical cross section for the
So there's several things that happens. Is one, once you interacted with a certain amount of material, there's no more light left for the rest of the particle. So it has to be small enough that both the light that goes through it and the light that go around it is affected by it. And if you're too small, and it's a lot like, it's the same as anyway, water waves or whatever, if you're too small, you're not moving. You're not affecting the light field. And you have to be much smaller than the wavelength of light. Yes.
If it's raining and the droplet size is
See.
much smaller, then also affect the visibility.
Well, it's not that then the droplets, once they get too small, very small, they're not falling. They're falling very, very slowly. Because settling velocity of droplets as well is going to be proportional to the diameter squared. So fog is basically suspended rate. It falls, but it falls very, very slowly. It's affected by turbulence much more. It stays suspended.
For like inside the cloud,
Yeah.
the droplet size is very less. It's not falling. And
You're right.
Weight is not that heavy. So if we are trying,
You're flying through a cloud.
yeah, if we go inside,
Yeah.
then for the it's below the cloud, the visibility is sorry.
Further, you can see further below the cloud than in the cloud.
For above the cloud, the visibility
In the cloud, it's the lowest.
and below the cloud, lower level of cloud and
I don't know. I don't know. I don't know. But my thought is not that good. But one would assume that if the droplet size changes in the cloud, the visibility changes. Just means that on this kind of audio, as long as the amount of water stays the same, the total mass. you have changes in mass, if you have more particle, then of course you can have more interaction. So you have to take this and multiply by the number. Yeah, I mean, in one versus the other. So this is for mass, and if there's more mass in the lower part of the cloud than above, then the beam attenuation there is going to be. So the last thing, and you don't have to do it now, the last thing that we're doing with this story is simply to calculate the attenuation, the visibility in. So how do we calculate that? How do we calculate attenuation? If I have a certain amount of light, let's say you're in your car, or somebody's driving towards you, there's a car driving towards you, and you're standing here. The attenuation due to this fog is going to go like the exponent of minus c times the length, the distance. So one optical length will be this c times l. This is the distance by which you're going to lose a third of your light, or one of the CL. So depending on these two, you can calculate how far you're likely to see a car that's coming towards you with its lights. And we're going to take a, so this is what I'm asking you in the next one. I'm sorry about this screen. I'm going to go and get a different adapter. This just drives me crazy. And so take a break, get refreshed, go to the restroom. When we come back, we'll do particle populations. Okay, now we're going to do a whole bunch of different particles together. Let's see how they operate. Any question on this? You'll ask me when not usually.
Yeah, it makes, well, I got 171.
Okay.
I guess makes sense. Okay, yeah. I thought that, so I was using the but it's indeed wrong because it's not exactly like this.
Yeah.
And I promise you, after this, I'm going to go jump in the water.
Oh, not a bad move. Yeah. Are you planning on taking the boat out?
I don't know. There's no swing, so probably not. But
So right now it doesn't see it at all. Oh. Come on, baby. Yes.
okay, staying more than the other one.
Yeah, already does.
Ah, yeah, it was really bad.
It was just crazy. So at one time, it seems to be going well. Let's see how it is.
Let's hope it stays.
Right.
Otherwise, it takes me.
Ooh.
You can keep that. I don't know.
I started with them too, so. It's really not very good.
Oh, God. Damn those.
on units.
Yeah, they don't pay both of them. Yes. Cool, cool. Okay.
Guys, there are cookies. If anybody wants cookies. Now is the time for the Cookie Monster. So finally, we got something that actually does work with the screen. So now it's not going to jump all over. So those of you who thought that there was unit conversion, they left the undergrad. Sorry. We're gonna on to the rest of the one. You stay inside.
Just died. It's okay.
There's one here.
It won't reach. I'll just go here. The name of the number. Oh, I'm sorry. Yeah, okay. I'm just gonna plug you down there. That's okay. I'm not.
So what I told you is if you know how much water you have, you can actually use what we got there to calculate the attenuation through a cloud with the numbers we got over there. The transmission, how much is transmitted in your fog? How far are you going to see that? But I'll move now towards the more applicable thing for you guys, for us guys. So now we have the population of spider mites. It's not a single, the have a certain particle size distribution. And here we'll assume a power law size distribution. But you can assume a Gaussian, you can assume a log normal, whichever you want. So we're assuming a power law size distribution. And we're going to play with it a bit. So the particles are ranging from 0.2 to 100 micron. Why do I do 0.2? Because I have a filter at 0.2. So I'm going to have 0.2 to 100 micron. I'm asking you to subdivide it to 35 logarithmic in the it's in the, don't worry, it's all in the software. 35 size beams. Assume a wavelength of 440 nanometers. That's again, that's air. There is 40. Index of refraction is 1.5. That's 0.01. And I said something about the size distribution. The size distribution I said here is this function. So the size distribution of PSD, this is the differential size distribution. So small d equals 5 times 10 to the 4th d to the minus 4. This is in numbers per ml per micron. Number per ml per micron. And now for this population, we want to sum up all the particles so we can get A, B, and C for that population. So I changed the name from Young to power law because we learn with time that it's a power law size distribution. Let's go to and find the. Let's go and find the in the Mie codes you got the one called power law. Do you have one that's called power law? Power law population, exactly. Let's see if I can find mine. So open that one up. Because power law population, let's open it to everybody. Here it is. What is this load metadata? I don't need it. I don't think I need it at all. So
You have this photo data.
you do have this file data, but I don't need to read it. I don't know. Am I calling the Mie code? Oh, so there was another one where I generated this. So sorry. So there's where did I do it?
I think it's called BH varied sizes.
Yes, it's BH varied sizes. So we start by running BH varied sizes part 2. Sorry. This is where we're generating our population. And then we're gonna save it as spider data and do it. So here is call BH varied sizes. So rather than do the input, I already give it everything I need. I have a D mean of 0.2. I have a D max of 100 microns. So I'm going to change that. So this is how I generate my optical population, my optical characteristic per beam. So now I'm going to take my size distribution, and for each beam of the 35 beam, I'm going to do the Mie calculation, and then I'm going to sum up based on, so I have, this is 0.2, and it's going to go until 100 micron. This is size. This is my size distribution, but I want to know for each size within these beams what the optical properties are, so I can sum them. So my D mean, this is my wavelength. Again, all the inputs of the call BH Mie, but I'm going to first. Instead of it asking me and me each time having to change the size, I can code it. It's going to be faster. So D mean is 0.2, D max is 100, and the number of size classes instead of 50 that I have here is 35. Now, this is something that you want to vary. So you do it, and this is true for any model you ever use. This is the discretization I'm going to start with, but then you can see if it makes a difference if you use a different discretization. And what happens is because things tend to be distributed log normally in the ocean, you want your beam sizes to change with size. You don't want them to be fixed in size. The bigger the particle, you want to have a bigger beam because there's less particle there. So this is a way, what I have here is a way by which I'm making 35 sizes in there that are growing like a power law. The beams are growing like a power law. This is here. Then I'm calculating everything as usual, doing my Mie calculation, normalizing my stuff to come out. And so now I'm ready to run it. There's nothing else I need to do. It's all in there. Put in, I'm getting 91 because I want every degree. And when you run it, the fun stuff is that it's going to give us a bunch of outputs that I want you to look at. So here is the run. It's calculating 35 different sizes, and it's going to end up with some figures. So these are the inputs as I told you, but we can do it with. We can change those. It's all here. My figures are on this side, they're not in front of you, so I have to move them. Come on, where are you? So these are the figures, the outputs that I get. So the first output that I get are the different Qs, different. So, and this is for one for each size. So this is QC, the efficiency factor for attenuation. You can see that it's asymptote 2, which is what it's supposed to be in geometric optics. QA and QB asymptote 1, exactly what it should be. And there's some oscillation, it can be bigger than 2. But you can see that from about 10 micron on, assuming QC equal 2 is not a very bad assumption with these parameters. What else do we see? Here on the bottom, I have QBB. That's much less intuition for that. There's some oscillation, it changes a lot with size.
Daniel,
Yes.
your QBB there, is that, a lot of these Mie codes put out what they call a backscatter cross section.
A radar backscatter.
But that's not our backscatter. Our backscatter is scattering from 90 to 180 degrees. And the Mie codes usually put out a cross section for scattering at exactly 180.
Yes.
Which is sometimes called the radar cross section, because they're interested in, like, hey, I'm looking at a raindrop with a radar, I'm just caring about what comes exactly backwards. So you go through these calculations like you did with the first exercise, and you've got so many fighter planes, whatever, you compute the absorption, the scattering, the attenuation, it all comes out fine. And then you try to compute the backscatter, and it's off by like orders of magnitude. And the reason is the Mie backscatter in your code may not really be our backscatter. So I was going to ask, what's your code?
So let's see what it is I'm plotting. I'm plotting QBB that's calculated from the back integral divided by the total integral. So it is the QBB. It's the optical backscatter. Efficiency factor. Yeah. So if you open the BH-Mie code, you'll see it there. If you open BH-Mie, I'll open it now. Oh, it's opening on the wrong one. You'll see that one of the things that it's here, there's this Q back, Q scat QX Q back, and the Q back is the radar. Here it's the radar backscattering. This one. Total scattering backscattering for given size. No, is this? Let's see what I did for it. This is the radar backscattering. Q back is not QBB, but the radar backscattering. No, it's written in the fine print in the back. So this Q back is not QBB. It's not the efficiency factor for backscattering, but I'm calculating it here in the code we just saw in the varied size, called the H varied size part 2 here. I am calculating it as the back integral of the VSF divided by the total. So that's why it's correct here. We plotted it. I want to show you the second figure. Yeah, so the figure here gives you BB over B for your particle. So this is QBB over QB is the same as BB over B. And you see it's much larger for small particles than it is for large particles. The amount of scattering we get in the back direction decreases with size.
What's the scale on the coordinate there?
0.1, 0 to 0.1.
Okay, because if you went up to 0.5.
That would be Rayleigh.
That would go to 0.5.
Yeah.
really small
Yeah,
part.
so very small particle, it should asymptote to 0.5 because that's Rayleigh scatter. Where QB, as much is scattered backwards as is scattered forwards. Okay, so now we have it for the 35 size distribution. Now we want to integrate them. So I saved these into the FIDO data. And now I'm going into, so I'm going to close this. And now I'm going to go and open the Paolo population. This one, and it's going to call the data in, it's going to load it in, and then it's going to integrate it to calculate beam attenuation, volume scattering function, and so this is going and the total C, A, B, and C, and also calculate B per beam, A per beam, BB per beam, C per beam, so you can see which contribute to which. So here are your VSF for each beam, and you can see how they vary. This is the volume scattering function for each beam. This is the total volume scattering function. When I sum all these with all their, I'm getting a smooth curve like the one you're going to measure with the LISST or with other instruments. These are a smooth volume scattering function for my whole population.
Manuel, can you show us how you got that graph?
This one?
Yeah.
It's in the code. It's in the code here.
Which code is that?
That's the code. It's called power law population. So it has the 5 10 to the 4th d to the -4, and then I'm changing it into particles in micron. I'm changing all the units so I'm consistent, so I can get A, B, and C that are consistent. Actually, if I do A here, this is my absorption for this population. This is my scattering population, and this is my attenuation for this specific population. That's summing all these 35 contributors. I have a whole bunch of other outputs. This output is absorption per beam. So you can see that smaller beams contribute more to absorption than the larger beams that I have in my logarithmic beams. Similarly, backscattering, I get more backscattering from this smaller beam than larger beams for Mie theory. And you see it's kind of jagged. When you see it's kind of jagged, you say, maybe I need to have a higher resolution so I can resolve more features than just 35 sizes in my size distribution. But often when you work with data, you don't have that, you don't have that resolution in size distribution. This is beam attenuation per beam and scattering per beam. And this again, here you see the resonance. You see that there's a certain size, in this case around 2 or 3 micron, that gives you the most beam attenuation. That's out of all these power law increasing beams for this population. Do we have any more figures that I did not talk about? That's it. So we saw, and this is, yeah. So here you can see that the moment you do population, you lose all these high resolution resonances that you have when you do very narrow population. Any question about this? In the code, let's go back. In the code, which, and you're talking about the power law? Yeah, here. There's what? Some B per beam. S11. S11 is the volume scattering function of each. And then I multiply it by, sorry, this is the phase function. So I have to if you multiply phase function at unit of inverse to radian, to get the VSF, I have to multiply it by B. So I'm basically summing for each beam the B and the volume scattering function for that beam. So I go one, so S11 actually has on one axis the VSF and the other axis is each of the and again, and I have here the 10 to, all these 10 to the 6 and 10 to the minus 12 and 10, all these are inverting units. So I finish with A, B, and C in inverse units. So what I ask you in the next exercise is take the same one. So we did it on logarithmic, we compared. But now what happened if I have a size distribution with D to the minus 3? So I have more big particles. Which things change in terms of contribution? So when you get to coastal environment, your power law tend to go more towards the minus 3 than the minus 4 oceanic. So so let's do that. Let's go from let's go back to this one. Where am I? Let's go to the MATLAB here and simply change to a minus 3 power law population, where we still have the same concentration. Sorry, minus 3. We still have the same concentration for the 1 micron particles, but now we have more big particles in there. So I can save and I simply run it. And suddenly you'll see you have more. This did not change much because it's per beam. All the per beam has not changed much. But now we have, because we have more of the big particles, suddenly they contribute more here than they did before. In C and in D, not in A and backscattering. And the total VSF is more peaked forward than it was before, because I have more big particles. And if I calculate my A, B, and C, if I do my A, B, and C, what do you think? Are they going to be higher or smaller? Higher, because I have more big particles. My A, maybe not by much, 0.17 compared to 0.04. My B, 0.24 compared to 0.06, and therefore my C, 0.42. So the one that increased the most is my beam attenuation, as I flattened and have more big particles in my population. Another question is, what happens if now I go only from 1 micron instead of from 0.2 micron in my size distribution? So this I can do, again, by going back to that population and just changing I can change the beams I'm summing over. So I can do it here, but it's going to be more complicated than simply rerunning the other one from 1 instead of 0.2. So let's say that I have a varied side called BH. Let's say that I have my filter is not 0.2 micron. Instead, it's, let's say, 0.7 micron. Okay, so remember your A, B, and C here. Remember this, about 0.17, because I want to run it with my GFF filter now instead of my 0.2 micron filter. 0.17, 0.2, 5, and 0.2. This is what I get when I have a 0.2 micron filter. Now I'm going to change to a 0.7 filter. Yeah, here, D min is going to be a 0.7. So now I'm a GFF, I'm doing this one, done. And then I'm going to run my population, my power law.
With the -4, the -3.
Same -3, because I already. And now I'm going to calculate again my A, B, and C, just to see how much did I lose from the fraction between 0.7 and 0.2. So I do A, 0.16, it was 0.17, not a big drop in A. How about my B? 0.24 instead of 0.25, not that much. I see 0.40, 0.42. Not a lot between these two for this size distribution, where I, relatively speaking, have more big particles. So for this size distribution, if my assumption are correct, using a GFF versus using a 0.2 micron filter, assuming that all the particles are the same, is not making a big difference. So again, this you can use that also for games like that, trying to understand what am I losing by using different. I lost. I mean, here it was like 5%. So relative to what I got in the other one. Okay. What next can we do with these? So we did this. If we change beams, so these are games you can do. If you have 100 beams versus 35, then I urge you to do it. So the next thing is this inverse calculation, what Rico and Morel did. You have a culture, you do optical measurements on it, and you want now to assign, you want to calculate what n prime or n might be. What's the thing? It's a refraction of my suspension. So now we go backwards. So let's say that we just ran an absorption with the ACS for Telasosira to the Nana and found that our absorption C76 is 4.4 inverse meter. Assuming all cells are the same size and they're all 4 micron, find the n prime for this, that find what n prime should be for lambda is equal to C76. It's going to be consistent with our measurement. And assume n equal 510 to the 4th cell, just like we did before. So what I suggest you do is use that the absorption equals QA times pi d squared over 4 times n. This is my absorption. I have 0.14. I know n. So I know n. I know g. I know all of this. And then, so now I can solve for what QA should be to give me that absorption. So QA, so what I'm saying is this following. We know that in the anomalous refraction approximation, QA is monotonic. This side. QA is this side. It's monotonic. And this goes to 1. I know that absorption equal QA times pi d squared over 4 times n. All this I know. If I know n because I do microscopy, I know g because I do microscopy, I know a because I have an ACS, I can get my QA. This I can get my QA. And then I can find what's my n prime that's going to give me that QA for a size that's 4 micron. So that what's going to happen if you have an n prime that's lower, it's going to take longer for us. The n prime is higher, it's going to get that. It's going to ask for to run faster. And so basically what we're doing is we're cutting through here and guessing what n prime is going to give us the appropriate QA for all 1. Okay, and you can have the computer do it for you, but it's kind of fun to do it. To just play with this until we get the right value. So how do we play? We go back. Window, where is mine? And it's much easier to do with using something like this guy, the AD, what I told you before. So we know lambda. What was lambda? Can you remind me? So AD, we'll go back to Q. So this is it. So my lambda is 6. Is what value? 676. 676. 676. What's my diameter in micron? Diameter. Is it diameter, Danny? Yeah, diameter. 4 micron. Okay. The real part doesn't matter for anomalous dispersion, so I can use whatever, and I'm going to use 0.1, and then I'm going to see what I'm getting for QA and compare it to what it should be. So what should be my QA based on our measurement? We said this was 0.16. What did we say this should be? This was 0.16 inverse meter. This what we had in the culture in the lab. What did we measure in the question? 0.1? 0.14. Pi, we know what it is. This is G, we said is 4 microns. So 10 to the minus 6, all this squared. The number of cells was 5 10 to the 4 per ml. So times 10 to the 6 per meter cubed. So we have all this, and from this you can calculate what QA should be. Let's do that first. So before I do this, before I'm running this, I'm gonna okay. So before I do this, I'm gonna do QA QA question is equal 0.14 divided by. Now I have everything on the right hand side. I have a pi. So I have here pi times d squared, so 4 e to the minus 6 square divided by 4. I have the n, which is 5 10 to the 10 to the 10 5 times 5 e to the 10. Anything else I need there? No. So this is QA. QA should be equal to this. So this is QA from the question. I get 0.22. My QA based on my measurement is 0.22. So now I'm going to adjust this n prime parameter until I can get 0.22. Okay, when I run it with 0.01, I'm getting 0.46. So now I'm going to put a 0.00. I'm going to put a 0.05 here. Let's see what that could give me. Sorry, 0.5, half of it, because I want a smaller QA. 0.27, I'm getting close. And of course, you can have, this is really close. I got 0.2289 versus 0.2228. So I might call it quit and say good enough for my n prime. So simply by playing with my AD code, I'm finding what's the n prime that's going to give me a QA like I'm measuring in the lab. In the lab, I measured A, from which I measured A, I measured size, I measured concentration, from which I can get a QA and then see what optical parameter will give me that same value. Okay, this is an inverse calculation. Now, sometimes in inverse calculation, there isn't one solution. It can be multiple, and then you have to bring in more information. In this case, you see it's monotonic. So I can, if I go now to 0.02 or 0.03, I'm going to pass below the value. Yeah, now I'm 0.17. And I wanted to get 0.2. So I'm a little less than 0.04. But so this is how Rico and Morel basically did a whole curve of n prime phytoplankton. Just went measurement after measurement, this similar calculation to this, with population of particle. You can do it with the population, it doesn't have to be single size. And then you can backtrack what your n prime should be in order to give you your observed optical properties. So these n primes, nobody ever, as far as I know, ever measured them directly. They infer them by inverse calculation.
All various work is done by
Yeah.
absorption, measuring absorption, measuring size.
So you measure absorption, you measure size distribution, and then you can derive what your n prime is. Clear? We can do the same for we can do the same for the real part of the image of refraction as well, except that then we have to be a little more careful. And the reason is you can find multiple solutions. So where's my, So here is for the same cell, it was found that beam attenuation is 0.8. Now vary n between 1.02 and 1.2 and find which is the most consistent with this observation. Notice there may be more than one solution. Choose the one that seems most reasonable. Okay, so here I can do it. So I said from 1.02 to 1.2. So here I can have a shortcut. And the shortcut will be like this. I'm going to say I can run it, I think, with a whole bunch of different in this real part. So we said 0.4 is correct, is the closest one. And now I'm going to put here, here. I'm going to try and put a whole bunch of 1.02, 0.01 to 1.2. So now I'm putting a vector, and I hope it will run. I don't know if it will run. And then I'll get a bunch of QCs. So I'll get a bunch of QCs, and then I would. So here are my bunch of QCs. These are in increment of 0.01. Then I will plot my C that I get. So it's going to be plot. And I'm going to put on the x-axis my the indices of refraction. And here I'm going to put the beam attenuation that I'm measuring. QC times pi times 4 e to the minus 6 square divided by 4. Put in brackets. So basically, what I'm going to plot now is beam attenuation times the size distribution, which is 5 10 to the 4th, 5 10 to the 10th, 5 e to the 10. So now, okay, I have one too many. So now I'm plotting the beam attenuation versus. How come I have? Oh, I see why. It's 0. Okay, the plot is here. So you see, I have several. These are the different indices of refraction, and I have several beam attenuations that will give me the same solution. The same solution will come with several of those. So in this case, I have more than one solution for my inverse problem. Let's kill all these and replot it. Okay, I plot it again. Now I should have only a single super beam. Why do I get 2?
Because it's all.
Oh, they're still all there. They're still all there. That's fine. Because I didn't kill them all. Now I should be able to see my one figure. Where's the figure?
It's
On your screen.
Oh, you're right. It's here. Here. So, and yeah. So I have more than one value of image refraction, but I know that for phytoplankton, it's most likely that it's going to be here, that my solution is going to lie with a true image refraction. So that's the one I'm going to choose. Or I'll do more measurements too.
Very smaller variant. Vary it by a smaller amount.
Oh, very the small amount is still going to be just in between here.
Oh.
So it's not going to, it will help me to get more exact value. But it's not going to change it from this group. Back to our inverse problems. Yeah, so yeah, value was 0.8. So actually for 0.8, maybe I did get a single one. 0.8, yeah, 0.8, there was a single solution. It was here. If I would tell you the value is 1.2 or 1.4, then you have more solutions for the beam C. For 0.8, there was one. Back to here. Another type of inverse could be for a whole population. A given population of inorganic particles, is distributed according to a power law between 2 and 30. If beam attenuation is 3 inverse meters, what's the amplitude of the sine distribution? So I have a sine distribution. I know the sine distribution, but I don't know how high or small it is. Then you can do exactly the same kind of calculation, just change it to get to the beam attenuation you're measuring. So all these things you can go back and forward. And this you can do yourself. There's no, it's really not difficult. Similar to what, and I think this is the last thing we have on.
Mhm.
Yeah. And so similar approaches can yield population size exponent or size ring of population given n prime, etc. So you can play these games. You can use other codes to do it. It just once they're in your hand, you can. It's a fun thing to do. We use it a lot when we calibrate backscattering sensors because the beads are extremely spherical. They're mistraceable in size. You get the size distribution of them, and we use we compute the beam attenuation of the beads. We measure the beam attenuation of the beads. From this, we get the concentration of the beads. We know how much beads we have in the water, and then we know how much backscattering a backscattering sensor should measure. The backscattering sensor gives us count, and then we calculate the conversion factor between counts and backscatter. So that's how you use exactly the same type of inverse calculation to calculate what's the concentration of beads in the water that should give you the beam attenuation measure. And you can do it in different wavelengths. You can do it. So it helps you constrain your suspension that you're calibrating. All good? Enough? Enough is enough.
I know you're all burning to dig into mathematics and game theory. So the place to start is the Ocean Optics web book, which has 3 pages and sort of outlines it, and that'll get you ready to go to Warren and Huffman's Scattering by Small Particles book, where he says, quote, those who work their way through the Mie theory will achieve virtue through suffering.
And the book is in the lab. The book is in the lab, just in case you want it.
I'm on the web book.
And I seriously doubt that more than 10 people have ever actually read Mie's paper.
The Mie's paper is from 1905. That's the book where the theory is outlined.
I thought through the pages.
It's in German, isn't it? Correct. It's in German.
There's a reproduction of the web book, the Ocean Optics book, a typical page of the paper. And it's nothing but equations. And then here and there, I'll say something like, it is obvious that, or it is easy to do. It is clear that, or you can convince yourself that in the rest of the page's equations.
But as you saw, several graduates of this class ended up using these codes for their theses or other papers they've done. So Rebecca Green used it to calibrate flow cyclometers, to look at size and forward scattered by beads for the calibration of a flow cyclometer. Tiho used it to come up with an inversion for size distribution in the ocean from space.
How
How
much do you believe in that?
I don't. That's personal.
And Sequoia, and I'm sure every other company, they buy these little polystyrene beads that are homogeneous spheres. They have a pretty well calibrated size, etc. So you mix up a gram of those in a liter of water and you stick the wrist in it and compare that with Mie theory, and the agreement's just essentially perfect. So that's just the final sanity check on calibration of wrist or whatever it is.
So Camila, the reason I don't believe is not because it might not work, is because I didn't see it yet compared to data that would do it. For me, the challenge with size algorithm is to do better than chlorophyll. Chlorophyll and size are correlated. It's not great, but it's like 0.6 R squared for those of you like R squared, or otherwise, you can do pretty well with chlorophyll to size.
So the profit you get what, an average size?
No, you don't get, I mean, we know that typically, it's not everywhere, typically as chlorophyll goes up, the average size of the phytoplankton go up. What is the exact relation to in diameter? I don't know. And I don't know if it's in papers or not. It might be in some of the next papers. So
It's ecological.
it's ecological.
The more stuff in the water, it tends to be bigger. Because there's more stuff in the water because there's more nutrients. But if there's more nutrients, there's bigger phytoplankton you can stay out and keep the smaller. So it's just, looking at ocean basin, gyre scale patterns.
So then the question is, can we do better than that? Can we, in times when it's a bloom of a small cell, can we tell there is a small cell that's blooming as opposed to more chlorophyll, bigger phytoplankton? And so far, I'm not convinced of any algorithm that's been able to outcompete chlorophyll. Now, the chlorophyll is great, but that's my yardstick. And everything correlates with chlorophyll in terms of ocean color. I mean, so the question is there information in the reflectance spectra, sufficient information that we can get something about size? And that's a challenge. And it might be, I mean, PACE will have polarimetry. So maybe when you add the polarimetry, you get more independent information that can help you get size and shape and other. Maybe the UV channels will help us. We'll see. And maybe it's possible. Maybe it's totally possible and I'm full of it because I didn't do it, so I'm negative to other people's work. I don't know. I mean, I'm just saying, it's just, but so far I haven't been convinced. So you have homework for tomorrow, getting small groups and discuss it through the evening. I know I'm going to go swim in the ocean. I've warmed enough in this room today. But any question, comments, anything about this? Yes. Yes.
Not on this topic.
Oh,
I have a offer from Mike Lomas to visit the Bigelow lab on Saturday. It is open to all of us. I need to get back to Mike about how many people want to come, and the time is currently set for 9 o'clock. Please tell me if you want to come and we'll figure out cars. Otherwise, I'm gonna grab a taxi over.
Also, can we make sure that we tell the kitchen if you're gonna miss a meal? Because I was here on Saturday with Kurt and there were 18 sandwiches out there and 2 of us eating. And so, he made a huge lunch thinking that as the original count that he had on Thursday, which I'm gonna ask you guys to put it up on the board, said that like 5 people were missing. Turns out everybody missed. So it just means that he could easily not fed me and Kurt. So just, just think about that. It's a lot of work for him to come in and make some beautiful lunch and be wasted on me. So just let it and it's fine. You don't have to be here. Just like make sure that you're not. Huh?
Do we have a deadline for
Thursday.
I think it would be nice by Thursday. Just so because there's a communication between the guy who's here on Thursday and the guy who's here on Saturday. They're different people.
And also they bring stuff from Upper Campus. So
Yeah.
that's the information. And Bigelow is highly recommended for those of you, for many reasons, but even architecture. You can see through the building into the ocean. When you stand in front of the building, it's really amazing. But that's, many of you work with phytoplankton. They have one of the largest living phytoplankton collection that people that grow cultures and stuff order from. That's very, very impressive. Okay. Stop.